So normally when we think of a switching regulator, we have these two resistors R1 and R2, and that's how we control the output voltage of a switching regulator. And we know this for typical formula, that is V out is equal to Vref multiplied by 1 plus R1 divided by R2, and Vref is typically like 1.3 volt, and then depending upon the value of R1 R2 you can set any value of V out that you need. But this is not the only way you can set the output voltage. You can also use an external voltage to control the output voltage, and in today's video we are going to see how we can do that and derive the formula for it, and we'll discuss the results. So let's see, we introduce a V control voltage. We can come from a DC regulator, or it can also come from, for example, a op amp, which in turn could be driven by a pulse width modulator. So the circuit is actually very simple, and what I'm going to do is I'm rearranging this circuit so that it looks like a simple Kirchhoff circuit. What I would do is I would simply make this V out, you can think of like this, V out and then R1 and then R2 to ground. I will make this battery, and then this is R2 to ground. This is our Vref, and then on this side we have this Vref point is connected to R3, and then we have a battery which we can call it a VC, or a control voltage. So what we can think of this circuit, and we can find out Vref in terms of VC and V out using simple superposition theorem. So what the superposition theorem says, that to find the voltage at Vref, we can find the voltage due to VC and then due to V out, and then sum the two. So first find out the Vref voltage due to V out. To do that, what we do is we short all the voltage sources. We short this one out, and then we find the voltage due to V out. So we have we call it Vref1, and that will be equal to R3. Now R3 and R2 are in parallel, so R3 parallel R2, and then this R1 is in series. So we can make it something like, so if you do the calculation, you will see that R3 parallel R2 divided by R3 parallel R2 plus R1. This is the voltage due to V out. Now we can also similarly find the voltage due to VC. We will short it out to V out here, and then we can find we call it Vref2, and that will be R1 parallel R2, and then this will be a voltage divider, and then we need to find out the voltage across this, which is R1 parallel R2. So that will be R1 parallel R2 divided by R3 plus R1 parallel R2, and then the total sum of these two voltages will be the voltage at Vref. So we can find Vref is equal to this plus this, and if you simplify this, you will see this is R3 into R2 divided by R3 plus R2. So, and then on the bottom side also R3 into R2 divided by R2 plus R2, and if you cancel this thing, I will directly write the result, R3 into R2 divided by this one will be R3 R2 plus R1 into R3 plus R1 into R2, R3 R1 plus R2 R1, and this is this, and in the same way we can write this one, and this time I forgot to write this one multiplied by this one was the voltage due to V out, so this multiplied by V out, and this is this one multiplied V control, and then so this is this times of V out, and plus this one will be in the same way R1 R2 divided by R1 R2 plus R2 R3 plus R3 R1 multiplied by V control voltage. And from here what we want to find out is the V out in terms of Vref and V control voltage. So let's do that. So we'll get V out is equal to this is Vref multiplied by R1 R2. This whole thing goes to the left. R1 R2 plus R2 R3 plus R3 R1, and then minus this R1 R2 into VC, R1 R2 into VC. So and then this whole thing will be divided by R3 into R2 here. I still keep this thing here, I just move this guy over here and then minus this thing. Now we can divide this whole thing by R3 R2, so we get V out is equal to Vref multiplied by R3 R2, R2 R3 gets cancelled, so this thing becomes 1, and this R1 R2 divided by R3 R2 becomes R1 by R3, and then this one becomes R3 goes away, becomes R1 divided by R2, and minus is R2 goes away, this is R1 divided by R3 into V control voltage. And right now we'll see how nicely this equation comes in, and then we'll discuss the result. So V out is equal to Vref. I will rearrange it and write it as Vref multiplied by 1 plus R1 divided by R2, and then what I'm going to do is I write this term as a separate and the rest of the things separate. Vref multiplied by R1 divided by R3 minus R1 divided by R3 into Vc. So if you for further simplify it, you see that Vref is equal to multiplied by 1 plus R1 divided by R3, and then I will write it as minus, I take R1 by R3 common, and I have Vc minus Vref. And this is the result that I wanted to discuss here. This is the voltage in the absence of this any control voltage. So this is now what you will be getting when you do not supply any kind of external voltage. And this voltage is reduced by an amount which will depend upon this voltage Vc, V control voltage. Now one thing we want to do is that in some what I am not sure, and then I will dig further into it. Typically this current could be also be flowing in this direction as well as in this direction. What I am going to do is I am only considering the case where current can flow in this direction, which means that this is a voltage source and not a voltage sink. The current cannot flow into this one. I mean, then you have to design a sink as well as source, a circuit which is sinking as well as sourcing current. I am only considering the cases where Vc is higher than Vref, which means that Vc is going to be greater than Vref. So that's why I have written this equation like this. Another thing you need to keep in mind is the ratio of R1 and R2. If let's say we keep it a very simple, where I keep R1 and R3 exactly equal, which is, let's say this is 1 kilo ohm and this is also 1 kilo ohm. Both of them are equal. In that case, simply this difference will guide how much is the voltage is going to get reduced.